So today I'm going to be talking about what is often called Pell's equation, but really there are probably some better names that we could call that. Based on the Indian mathematics that we're going to be looking at, so the equation itself, I haven't written it on the board yet, I'm about to. The equation itself goes back to even Diophantine. But the two Indian mathematicians, and there's other people as well, sort of lost to history. But the ones we're going to look at as we talk about this, I will write their names up on the board in just a moment. They're the ones that made significant progress in studying this and essentially solved the problem. I mean, they essentially solved the problem. They didn't have a proof presented for it. So I guess if you don't, if aside from that, they had the problem solved. But I think, I'm not even sure. Well, anyways, so once we look at the proof, it'll kind of be clear, like, well, maybe they actually did have the proof. Okay, so let me just write what this equation is without anybody's name. The equation itself, so we're going to fix an integer in. We're going to fix an integer in, and we want to solve the equation x squared minus n y squared is equal to 1. And n is going to be some fixed positive integer. And so what this equation gives us, it's going to give us a hyperbola opening like this. And we want to find solutions in x and y. So integer solutions in x and y. In other words, we want to find integer points on the curve. Now, of course, you can imagine, we want to find integer points on the curve. That is points with integer coordinates. I'm not going to talk too much about motivation for why we would want to study this in this video, but I do want to mention one thing. Notice that if I divide both sides of this by y squared, I get x squared over y squared minus n is equal to 1 over y squared. And so what this is telling me is that x over y is an approximation to the square root of n, with the error here being 1 over y. Okay, or 1 over y squared if you square it, and don't look if you square it and look at it that way. So this gives us a way, if we can find integer points, then this gives us a way to approximate the square root of n. And then as y gets bigger, if x and y have no common factors, as y gets bigger, this error is going to go to 0. Okay, anyways, that is one motivation for this. I'm not going to talk about that. I'm going to talk about the methods that were discovered. Primarily, I'm going to mention two mathematicians to find solutions. So the first one that I will mention is Brahmagupta. He was able to solve some of these problems for some certain values of n and came up with a method that he was able to, given one solution, come up with more infinitely many solutions. And then there's another one, Bhaskara, who was able to come up with a method for finding solutions to equations like this for any value of n. And it's an algorithm that he comes up with. It's an iterative algorithm, so there's sort of like the beginnings of induction there as well. I'm going to give a sort of sketch of why that algorithm works, but that's going to be several videos from now because I haven't even given you the algorithm yet. Okay, so there is sort of central to Brahmagupta's method for creating, for both finding solutions and creating solutions is this idea of composition, and or composition of solutions or composition of triples. And to understand that, we first have to make this problem a little bit different. So we have to sort of relax our condition here. And now what we want to do is find triples. I'll just call it x, y, k, such that x squared minus n y squared is equal to k. So it's exactly like this problem, but instead of having a 1, we have a k. Okay, and so we are going to be able to do a couple of things here. When we see the algorithm that he creates, we're going to see how we can sort of take triples, modify it, and kind of systematically reduce this k. Not quite, but we basically want to systematically reduce this k until we get to 1. It's more complicated than that. That's sort of the general idea. But what Brahmagupta has given us is this wonderful operation that we can do on these two triples that he calls this composition operator. Or we call it this composition operator. He called it something else that did not mean that. Anyways, so to show how this works, he first sort of realized there's this algebraic identity. It doesn't really have anything to do with triples. It's just like an algebraic identity. I'm not going to prove this identity for you. There's really nothing to it. I mean, the identity itself is not deep. It's just a matter of expanding things. But the point is, realizing that this identity is true is sort of one of the linchpins to all of this. So the identity is the following, and this works for any 3 numbers, any six numbers, really any 7 numbers. Let me just write it and stop rambling. It'll make a little more sense. So x1 squared minus n y1 squared times x2 squared minus n y2 squared is equal, and I need to come down here, is equal to x1, x2 plus n y1, y2, and I'm going to come down here to the next line, minus n x1, y2 minus, plus x2, y1, plus x2, y1, like this. So we have x1 squared minus ny1 squared times x2 squared minus ny2 squared is equal to x1, x2 plus ny1, y2 minus n times x1, y2 plus x2, y1. Now, one thing I also want to point out here, in this identity, if we think what's going to happen over here, actually, I left out something very important. There are squares here and here. So if you think about what's going to happen when we expand this, when we get the cross terms, we're going to get plus 2 times x1, x2 in y1, y2. And what's going to happen down here is this is going to cancel with the when I square this, I'm going to get 2 x1, y2, x2, y1, and then multiply it by n. So the cross terms, if you want to call it, the ones where you multiply those by those when you FOIL, are going to cancel. So notice what's also going to happen. If I do a minus here as well, the square terms are going to stay the same. The minus terms are going to be minus, but they're still going to cancel with each other. So I can either have this identity with pluses there or with minuses there. So it's just important. If I have plus there, I have to have plus here. If I have minus here, I have to have minus there. So I can't do minus here and plus there. Okay. And there's other ways to write. These identities as well. Okay. So like I said, this is just a pure kind of algebraic identity that has nothing at all, in principle, to do with what we're studying. It was motivated by what we're studying, but this is true no matter what the relationship between x1, y1, x2, y2, and n are. However, here's how we can apply it to the present situation. So there is this operator that Brahmagupta, or operation maybe I should say, that Brahmagupta introduced, which we call composition. There's a sort of plus composition and a minus composition. And I'm going to use my own notation here. You can decide for yourself whether you like the notation or not, but it's going to be the following. So we've got x1. So if I have a triple x1, y1, k1, and they could, in practice, they are going to be triples like this, but they don't have to be. x1, y1, k1, we're going to have a plus composition. There's going to be minus 1, 2, x2, y2, k2. This is defined as the following. The little colon there means I'm defining it, and it is defined in the following way. It's going to be x1, x2, plus in y1, y2. Okay, and then so it's going to be another triple, I should say. So we're going to take two triples, add them together in this weird composition operator, and it's going to give us another triple. And then we're going to have x1, y1, plus x2, y2, and then k1 times k2. And then there's going to be a minus version where we put minuses there and there. So we're going to have a minus version as well. So the minus version is x1, y1, k1. I'll do minus. I've not seen this notation that I'm using here, so like I've not seen this notation before with the circle plus and circle minus. I mean, I've seen circle plus. I don't know if I've seen circle minus, but I've seen those symbols, but I've not seen them used in this manner here. So this is non-standard notation. Just to warn you. x1, x2 minus in y1, y2, and then we're going to have x1, y1 minus x2, y2 minus x2, y2, and still times k1 times k2. Okay, so I'm going to have that there. I'm going to have to start erasing things, but here's what I want to show. I'm just going to kind of talk through this. If x1, y1, k1, and x2, y2, k2 are triples, triples in this sense right here. I'm going to call them Brahmagupta triples. I don't know if anybody else does. Again, that might be just me. If these two are Brahmagupta triples, which I'm just going to abbreviate now as BT. If these are Brahmagupta triples, then so is their sum and their difference. Okay, so is their sum and their difference. Okay, and the idea is going to be this identity over here, because we see what's going to happen here. This right here, that when you square it corresponds exactly to this. So let me just back up. What does it mean for these three to be a triple? It means this thing squared plus n times this thing squared is equal to that thing squared. So the first entry squared plus n times the second entry squared is equal to the third entry. Okay, so x1, x2 minus n, y1, y2, that corresponds exactly to this, and we're squaring it. Then we're going to do plus n times the second entry. Notice this is the second entry here. Or I guess I'm doing the plus. So let's look at the plus. Okay, that's the first entry. It's right here. The second entry, x1, y1. Whoops. Man. Sorry. This is going to be annoying, but I'm not making this video again. x1, y1, x1, y2 plus x2, y1. And I screwed it up down here as well. x1, y2 plus x2, y1, like this. Let me just make sure I have that. X1, y2. Just needed to make sure I had it in the correct order. Okay, so if you do that, that's this, and then plus n times that term squared. That is the term that we're squaring is the middle one. And notice what you get. You get x1 squared minus ny1 squared. Well, x1, y1, and k1 are triples. So it means that this here is equal to k1, and similarly, this is equal to k2. And so it shows, what this shows, at least for the plus solution, and the same thing goes for the minus solution, that if x1, y1, and k1 are solutions, and x2, y2, and k2 are solutions, or sorry, Brahmagupta triples, then so is both their adding composition and their minus composition. Okay, so then maybe it's going to become clear now how, given one triple with k equals 1, we can come up with another triple. So let me just do that over here. So if, let's say, if x, y, 1 is a triple, a Brahmagupta triple, and this is like the winning triple because k is equal to 1. That's the one we're looking for. X squared minus ny squared is equal to 1. So if we have found 1, if that's a Brahmagupta triple, then what we can do is just sum this or compose it with itself. Then so are x, y, 1. We can either do the plus 1 or the minus 1. X, y, 1. And notice now the formula is going to work out very nicely. We're going to have x1 times x2, so that's just going to be x squared. X1 times x2, that's just going to be x squared. X squared plus n, and then y1, y2, y squared. Okay, and then it's going to be x1, y2 plus x2, y1, but the x1 and x2 are equal, and the y2 and y1 are equal. So this is just equal to 2 xy, and then 1 times 1 is just equal to 1. So this is just the plus solution, the plus one. Now, if you do the minus one, notice what's going to happen for the minus one. Well, this right here is going to give us, when we plug that, this is going to give us x squared minus ny squared, which would be k. And now we're going to get xy minus xy, so this is going to be equal to 0. So the triple then is just going to be k, which is 1, and then we have 1 there. So the minus 1 technically gives us a triple, but it gives us the trivial triple 1, 0, 1. So we don't care so much about that one. Okay, so if we have two non-trivial triples like this, we can create another triple, and of course we can do things like compose this with itself, compose it with that, and get an infinite number of triples this way. Every time we do this, we're going to get a bigger and bigger triple. These numbers are going to grow bigger and bigger and bigger, but this is going to stay 1. Okay, so this is how we are able to, given one triple with xy1, which again, the ultimate goal is to solve the equation x squared minus ny squared is equal to 1. Excuse me. That is, find triples x, y, and 1. Sorry. If we found one solution, then we can find infinitely many solutions from that one solution. Okay. This video has already gone on a little bit too long. In the next video, I'm going to show you how we can figure out how we can get a triple, a 1 triple, an xy 1 triple, if we have an xy 2 triple. So I'm going to show you how from an xy 2 triple we can reduce that to get an xy 1 triple. Anyways, like I said, this stuff can be very tedious. I think it's very interesting, and I hope you'll spend some time thinking about it as well, and I hope you find it interesting.